Hello everyone, and welcome to session number 11 of this set of videos created to explore programming applications in reinforced concrete. In this session, I will present a Maple document that is capable of designing flanged reinforced concrete beams carrying positive bending moment. A flanged beam here can be either a T or an L-shaped cross-section, where the flange is the part of the slab system that is cast monolithically with the underlying webs of the beams. Positive bending moment means that the tension steel will be placed in the web at the bottom of the cross-section, while the compression zone will be located at the top of the cross-section. The compression zone can either be rectangular in shape, when the depth of the Whitney rectangular stress distribution is inside the flange, or a T or L shape depending on the type of the beam, when the depth of the rectangular stress distribution is greater than the flange thickness. Let's look at the Maple document that is developed for the flexural design of flanged reinforced concrete beams carrying positive bending moment. On this side here, we have the input parameter zone where the user will insert all the parameters required for the design process. Let's go through these parameters one by one. First, we have the required factored moment, then the initially assumed diameter of bar, yield stress for steel and compressive strength of concrete, concrete cover, diameter of stirrup, the range of rebars to be used in the design process. Then we have the design economy parameter, which is nothing but the design strength divided over the factored moment and presented as a percentage. The user is also required to insert a value for the depth of the beam in the case where the depth of the beam is predetermined. Such cases can evolve when the depth is restricted by the architect or by some serviceability requirements. In such a case, the user inserts a value for the depth of the beam. If the value of the depth of the beam is not known and is to be designed by the Maple document, then the user can insert a 0 here, and the Maple document will determine the depth of the beam based on the length of the span center to center and the support conditions of the span. The user is also required to insert the thickness of the flange, which is nothing but the slab thickness. The support conditions for the beam span can either be simply supported, one end continuous, both ends continuous, and cantilever. The user can then either insert a value for the beam web width or insert a 0 for the width of the web so that the template will design the width of the web and take it as h/2. The user is also required to insert a value for the effective width of the flange if the effective width is known. The value is inserted as b given, and if the effective width of the flange is to be designed by the Maple document, then the user can insert a 0 for b given, and the document will calculate the effective width of the flange based on the conditions of the ACI code, one of which is the clear distance between beams. Let's run the first example using the parameters that are shown on screen by clicking enter. These here are the initial design parameters. The depth of the beam is taken as 400 millimeters. The thickness of the flange is 150, inserted by the user. The beam's web is 300, inserted by the user. And the effective flange width is 1000 millimeters, also inserted by the user. This here is the design alternatives matrix. We can see that we have 9 design alternatives. Each one of these design alternatives is for a specified bar diameter. We can see that the first 7 were rejected. The 8th design alternative is adequate and does satisfy the ACI code requirements and the requirements imposed by the user, whereas design alternative number 9 is rejected. I would like to point out here that this Maple document is smart as it tries to perform the initial design in the first design cycle, but if the design cycle fails, another design cycle is performed in order to fix the first trial of the design. If the second cycle of design is a failure as well, then the template will state that for the specified bar diameter, the design has failed. This here is the design section, which in this particular case is the only section that actually passed the design process. So the results for the chosen section are shown here. Then this here is a plot of the cross-section that shows the dimensions, the depth of the compression zone, and this here is the ductility status of the beam, indicating that the beam is in the tension controlled zone. Let's change some of the input parameters and see what happens. Let's change the support conditions of the beam span from 3 to 2, meaning that we are changing the span support conditions from both ends continuous to one end continuous, and click Run. You can see here that the depth of the beam has been changed. This here is the design alternative matrix. This here is our chosen cross-section, the plot of the cross-section and its ductility status. Let's make a couple of more modifications. Let's give a value here for h given. Let the depth of the beam be specified by the user, and change the effective width of the flange to 800 instead of 1000, and click Run. These are the initial design parameters. This here is my matrix, my chosen section, a plot of the cross-section with dimensions and the depth of the compression zone, as well as the ductility status. If we go back and change the required moment to 200, change the type of analysis to 2, indicating that we would like to design an L-shaped cross-section. Let's change the depth of the beam to 400, given by the user. Let's also change the thickness of the flange to 70. I want to show you a certain output of the design, and let's say that the effective flange width is 400, which is very small, but let's check it and see. Again, these here are my initial design output parameters. This here is our matrix. This here is the chosen section, and you can see here that we have designed an L section. For this particular section, the depth of the Whitney rectangular stress distribution is greater than the flange thickness, and thus the compression zone is actually an L-shaped compression zone, and the figure next to it is the ductility status of the beam. Let's go back and make some more changes to the input parameters. Let's change the required moment to 250. Let's design a T-shaped cross-section. I'm going to increase the flange thickness to 80 and increase the effective width of the flange to 500, and run. Again, these are my initial design parameters. Here I have my design alternatives matrix, my chosen cross-section. This here is a plot of the designed cross-section. Again, this here is a T section, and the depth of the Whitney rectangular stress distribution is greater than the flange thickness, and thus we have a T-shaped compression zone, and this here is ductility status. For our last design attempt, let's go up here and change the required moment to 600. Let's change the depth of the beam to 500, Let's have the beam length center to center as 6.4 meters. Increase the flange thickness to 180. Specify 0 as my BW given. I don't want to insert a value for the width of the web of the beam. I want the Maple document to design that value, and a 0 for the effective width of the flange, so that the Maple document will calculate the effective width of the flange based on the ACI code requirements. And we click run. Again, these are my initial design output parameters. This here is my design alternatives matrix. You can see that only one section made it, so it's going to be my design section. This here is the plot of the cross section with the dimensions, and this here is its ductility status, indicating that the section is in the tension controlled zone. This concludes our session. Thank you very much for being with me again, and I hope that I will see you in the subsequent sessions. Best wishes.